Okay. Alright, so talk a little bit about Chapter 8, inferences based on two samples, confidence intervals, and tests of hypotheses. I'm just going to focus on means right now, as well as some other things to try to help you with the homework. I extended it by a week since I didn't have a chance to post a video this week. So if you guys have any problems with the homework or the quiz, let me know and I can post another video more specific to your needs. So we're going to try to answer questions like these. So who gets higher grades, males or females? Which would allow us to compare the mean grade for males to the mean grade for females. Thus we have two samples to compare. And that's kind of the premise of what we're looking to calculate out our confidence intervals in our hypothesis tests. We can examine differences in several parameters, just like doing the single sample hypothesis test. We can look at a difference of means, difference of proportions, or a ratio of variances. In the future, when we get to analysis of variance, this is going to be very important, but that's in another couple weeks. So if we have a large sample size, then we will use a z-test to calculate our confidence interval. If we know the true population variance, then we will use the formula for known variance, and if we do not know the true population variance, then we will substitute in the sample variance. Either way, we take the difference in the mean and add and subtract the z-value for the particular confidence level, times the square root or a sample variance divided by the sample size plus the second variance divided by its sample size. So I've created a small spreadsheet to help us out with that. So here is that formula, difference in means plus or minus z alpha divided by 2, square root of our variance divided by their sample sizes. So I've calculated it out based on if it is a 90% confidence interval, 95% confidence interval, or a 99% confidence interval. So you just put in your sample sizes here, your sample means, and your sample variances. So our hypothesis test for two means will be very similar to previous setups for hypothesis tests. In general, we assume that there is no difference between the means. Hence, D we expect to be 0. Which makes it easy down in this formula when we calculate our Z statistic because we're subtracting by 0. So it's really just the difference in means divided by their pooled variance. So D will be 0. On this slide, we conduct a directional hypothesis test where we believe the hypothesized value is less than 0. To get the z value to test our hypothesis, we divide the difference in the means, x bar 1 minus x bar 2, by the differences in our variances. D is almost always 0 because we are generally assuming that there is no difference. The difference in the means is found by taking the square root of the variances divided by their sample sizes. A two-tailed test is very similar. We just change the critical value for rejection by dividing z by 2. So the only difference between the two is our z alpha and our z alpha 2. So let's do an example of a difference in means, confidence interval, and hypothesis test. You're a financial analyst for Charles Schwab. You want to estimate the difference in dividend yield between stocks listed on the New York Stock Exchange and the NASDAQ. You collect the following data. You have sample sizes of 121 and 125, means of 3.27 and 2.53, and standard deviations of 1.30 and 1.16. What we'd like to know is what is the 95% confidence interval for the difference between the mean dividend yields. So, like I said, I have created an Excel spreadsheet to help solve this problem. Take our values and we can put them in here. It will perform this calculation, and this 90% confidence interval, 95% confidence interval here, which is what was asked for, and 99% confidence interval. So same data, same setup. If our hypothesis is that the average yield is different, so using the same data, let us calculate out a hypothesis test. Oops, go back to the spreadsheet. Here we can calculate our z value, and if our alpha value is 0.05, so we would be interested in a critical value greater than 1.96. So our value is greater than our critical value of 1.96, so we can reject the null hypothesis. This is a lot more useful if you actually have the raw data to compare, because there's things we can do in Excel other than just calculate them out, but we can talk about that later. So calculate out our z statistic is greater than our critical value, and thus we can reject at 0.0. There's evidence that there is a difference between the means of the two stock index, or the two stock markets. So if we have a small sample size, we have to calculate it out a little different, and of course use t statistics instead of z-scores. Now, formulas are similar. The main difference is that we multiply the squared standard deviation, or the variance, which is called the pooled standard, or the pooled variance here. That's what the P stands for. I've also created a formula for calculating that out. Let me move that up there. So this is how we calculate out our confidence interval. This is how we calculate the pooled variance that is used. And of course the t statistic that we'll need to do our hypothesis test. So slightly different formula. We multiply the pooled variance times the inverse of our two sample sizes. And same thing if we have to use t-tables now to look up the critical value and our so let's calculate that with an example. Okay, so we have a smaller sample size this time, less than 30. We will want to use a t-test instead of a z-test. So you're a financial analyst for Charles Schwab. You want to estimate the difference in dividend yield between stocks listed on the New York Stock Exchange and the NASDAQ. You collect the following data. Sample size is now only 11 and 15. Our means are 3.27 and 2.53. Our standard deviations are 1.3 and 1.16. Interested in a 95% confidence interval. So calculate that out here. I've set that to calculate here the same way. You put in your values. And it will calculate it out. You need these degrees of freedom to get your T alpha 2. So it calculates out your degree of freedom and your alpha divided by 2, where you can then go to a T table to look it up. 24 degrees of freedom at the 0.025. So our critical value is 2.064. So we use that to calculate out our confidence interval, as it is that value there. Okay. We can also use or utilize the same data and determine a hypothesis test to determine if there is a difference in average yield. So assuming normal populations and equal population variance, is there a difference in average yield? So to find, we know that our critical value is 2.064. Now we just need to calculate out our t statistic to determine if it is less than or greater than. So to calculate it out, like I said, d will almost always be 0, so you're subtracting from 0. Take the difference in your means and divide by the square root of the pooled variance times the inverse of your sample sizes. You'll notice it's the same part of your confidence interval. This part here is the difference in the means, and the denominator is the same as what you multiply by your critical value. So calculate this out, we get a t value of 1.5. It is less than 2.064 from the t-table, and thus we cannot reject the null hypothesis, or we fail to reject the null hypothesis. So do not reject. There's no evidence that there is a difference in means for the average yield, at least not with such a small sample size. Okay, so the next question, question 9 on our homework, is how to determine sample size for a given margin of error. We can do this if we have our confidence level of interest, the variance, and our margin of error. So let's do a sample size example. We have a difference in means that we're interested in at the 95% confidence level. We have a margin of error we're willing to accept of up to 5.8. And we have two variances, 12 and 18. So we have a margin of error, I think it was 5.8. Variance 1, variance 2, it should different. Let's see. 12 squared. Oh. Supposed to square those values, sorry. What's this? This was up 95% confidence levels. So. Okay, now it works. Fortunately, I haven't uploaded this to Blackboard yet. All right. So we were expecting an answer 54. I put a roundup formula based on how this calculates out, and at the 95% confidence level, we would need a sample size of 54. All right. Okay, and the last subject I want to talk about is the F-test. The F-test will become very important to our analysis of variance that we're going to talk about very soon. That's also called ANOVA. It will allow us to compare multiple means later, but right now we're just going to focus on comparing two variances and determine whether they are equal. Higher variance always goes on top. So if our sample 1 variance is higher, it goes on top, or if our sample 2 is higher, then it goes on the top, or is the numerator. Let's see. But we will compare this to yet another table called the F distribution table. We need our degrees of freedom. We're given V1 is the numerator degrees of freedom, and V2, use these to look up the F table. So say we have another example. Our financial analyst for Charles Schwab. You want to compare dividend yields between stock listed on the New York Stock Exchange and the NASDAQ. You collect the following data. We have a sample size of 21 and 25, means of 3.27 and 2.53. Standard deviation is 1.3 and 1.16, so it's all the same. We want to know, is there a difference in variances between the New York Stock Exchange and NASDAQ at the 0.05 level of significance? So our interest is, are these variances equal? We're given our degrees of freedom are 20 and 24. So we look those values up on an F table and we get 2.33 in the right time, and we can calculate our F statistic where we take the variance, the higher variance, and divide by the lower variance. We get 1.25, which is less than 2.3, and thus we cannot reject, or we fail to reject, the null hypothesis. There is no evidence that there is a difference in variances. However, if we come to your question 10, I suggest you use this F table to assist. Particular question that I had was this one. For each of these cases that follow, identify rejection region that should be used to test whether these variances are equal or not. V1 is your numerator degrees of freedom, and V2 is your denominator degrees of freedom. So what you have to remember is you have to divide each of these alphas by 2. So 0.2 divided by 2, so we want to look at 0.1. If we go to an F table, the website I sent you to, two-sided 2. So if it was divided by 2, then it would be 0.1. So your first table we will look at, if your numerator or V1 degrees of freedom is 8, you go down the 8 column until you get to 30, which is 1.88, which was the critical value for the right-tailed side. For the second question, 0.10, for a two-sided 0.10, or for a one-sided 0.05. Idea. Our numerator degrees of freedom is still 8. We go down 8 until we get to 30, and it is 2.27 is the critical value for the rejection region. For alpha equals 0.05, two-sided is 0.05, and for the one-sided or right-tailed 0.025, same idea. We go numerator degrees of freedom is 8, we go down to 30, 2.65 is the rejection region for that level, or that level of alpha. The last one is alpha equals 0.02, which is the next table. Two-sided 0.02, one-sided 0.01. We go down the numerator degrees of freedom of 8, so we follow this column down to 30, which is 3.17. Hopefully that helps you learn how to read an F table. In the future, when we actually run analysis of variance, this will all be calculated out for us, but this is just trying to get you to understand where F values come from and how kind of fundamental knowledge behind the F distribution as it is used for ANOVA, which is what we're building up for. Hopefully this helps you with your homework. Like I said, if you're having any other problems with your quiz, let me know, and I would be glad to record another video to help you understand any particular topic. And best of luck.